Hey, what's going on everyone? We are now back for part 2. Last time we derived Gruneisen's law for non-interacting particles in a box. In this video we will use statistical mechanics and the form of our single particle energies to determine the expected value of the total energy. To calculate the total energy we need an expression for it. In part 1, we saw that we could rewrite the expression for the total energy as a derivative of the natural logarithm of the partition function with respect to our inverse temperature beta. This tells us that to proceed, we need to calculate the partition function if we want to calculate the total energy. Our first observation is that the particles are not interacting with each other. If we only had one particle, we could imagine evaluating the partition function only for that particular particle. Since these particles are not interacting, usually we could calculate the thermal distribution for each individual particle in this case and be done with the total calculation. To see this, we can imagine labeling each vector n by the index I for each individual particle. We can then write the energy as a sum over the individual particles' energies since they are non-interacting. This allows us to break up expressions in the following way as products of exponentials over the individual particles' energies. This might lead us to the conclusion that we can fully separate the problem. Fully separating it due to the non-interaction would allow us to write the full partition function as just the product of all of the individual ones being identical to each other. This then allows us to write z, the partition function, is equal to z1, the single particle partition function, to the power of the number of particles, big N. But this turns out to not be quite right. There is a subtle issue here we must address. The particles are indistinguishable. So for example, each energy for an individual particle is specified by the indexes n1, n2, and n3. We can imagine a scenario where two particles have energies labeled by the integers 1, 5, and 8, and the other particle with 3, 6, and 4. We can also have the opposite case. The key thing to take away here is that these situations are actually the same. These particles cannot be distinguished, so counting these two situations as unique would be overcounting the number of configurations our system can be in. Therefore, we need to correct the overcounting. This correction is actually a standard counting problem. How many ways can we distribute n energies to n particles? The answer is n factorial, the total number of permutations. From here, to avoid overcounting, we can now say that the partition function can be written in terms of the single particle partition function. It is written as 1 over n factorial to avoid overcounting times the single particle partition function to the power of the total number of particles, big N. So we have reduced the problem of calculating the partition function for the entire system to calculating the single particle partition function for an individual particle. A great simplification to the problem. Okay, we have an expression of the sum of many exponential functions where the square of the natural numbers shows up in the exponential function. Our first task is to convert this sum into an integral, and to do this we will introduce a new variable for each n. We define k1 to be the square root of all of the constants in the exponential times n1. We do this with the constants out front so that we can simply rewrite the partition function. This new summation sums over all possible values of k1, k2, and k3. Now we can break our partition function up even further and see that only considering k1 is sufficient. Rewriting it, we can get the following expression where we have decoupled all of the summations. Since there is really no difference between each value of k, we will focus on the first summation. Let us look closer at k1 as a variable. The first thing to note is that due to n1 being a positive integer, the difference between two neighboring points of k1 is always given by the following expression. Delta k1 can be small for a number of reasons. Firstly, if we have high temperature, which we will assume here, beta is quite small. Secondly, Planck's constant is also quite a small quantity. If our particles are big-ish, the mass m is large, shrinking delta k even more. And lastly, if the side lengths of the box are relatively large, this also shrinks delta k. Putting all of this together, we see that k is a positive number that goes from roughly 0 to positive infinity, and the spacing between points is extremely small in the regime we are interested in. So we can rewrite our sum for k1 by introducing delta k1. You'll note that the part in the summation looks like a Riemann sum. So then we can approximate this sum as an integral, giving us the following expression. This Gaussian integral has a well-known value and is equal to the square root of pi divided by 2. Putting this all together, and remembering that we also had k2 and k3, we can finally state the full expression for our partition function z. We say that the partition function z is 1 divided by n factorial times v divided by lambda cubed to the power of n, the total number of particles in our box. Lambda is something people call the thermal de Broglie wavelength, and it's simply a convenient re-expression of our 1 over delta k. Now back to our goal of the energy. We need to take the natural logarithm of this partition function that we have derived. Plugging our definition of the partition function into the natural logarithm gives us the following expression. Only the first term depends on beta, and the second term will disappear when we take the derivative with respect to beta. Expanding everything out and taking the derivative ends up giving us the following expression. Unsurprisingly, plugging this back into Gruneisen's law gives us the ideal gas law, completing our goal of deriving it from first principles. We have therefore confirmed that under the assumptions of high temperature and assuming that we are somewhat in the classical limit, we could use the equipartition theorem to finish off our proof in part 1. We have now justified the ideal gas law through first principles. Through ignorance arguments, we arrived at the thermal distribution in the video on Jane's principle of maximum entropy. In part 1 of this video series, we derived Gruneisen's law through the thermal distribution and the scaling behavior of non-interacting quantum particles in a box. In part 2, we have then used the thermal distribution to calculate the energy of our gas, arriving at the famous ideal gas law. As always, guys, thanks for watching. If you like the video, feel free to like, subscribe, and leave a comment below.